In 1996, a group of scientists made the discovery of a lifetime. It was a rock, but a very special rock found sitting on top of the ice sheet in the Allen Hills region of Antarctica. The rock was special because it was actually a meteorite blasted off of Mars from an impact long ago. That rock wound its way through the solar system before falling to the Earth. Millions of years later, it worked its way to the top of the ice, where it sat for easy pickings. Geologists found the rock itself way back in 1984, and over the years it attracted a fair bit of study. After all, it's not often that a piece of Mars literally falls from the sky. But in 1996, the group of scientists examining the rock found microscopic features that looked like fossils. There were these tiny little tube-like features that, no joke, looked like worms made out of stone. It seemed that we had our first evidence for life outside the Earth. The news was a huge explosion. NASA held a press conference. The president at the time, Bill Clinton, made a speech. Everyone talked endlessly about the tantalizing possibility. No, it wasn't the kind of life that we could talk to or share cheese recipes with, and it was very possible that Mars had been dead for billions of years, leaving a planet of nothing but fossils. But man, just the thought that we may not be alone in the universe was too good to ignore. That we had finally found a friend, a microscopic fossilized friend, but in this universe, you have to take what you can get. Then came the most annoying group of people in the world. Other scientists, the skeptics, the analyzers, the pick-aparters. They found a way to generate these tunnel-like structures without life at all, just through simple chemical reactions that would be favored in the exotic Martian climate. Just like that, the thought of life on Mars vanished in a puff of wishful thinking, and everyone pretended that the embarrassing episode never happened. Since then, we have yet to find confirmed evidence for life anywhere else but the Earth. But we're not done. And the solar system has some places that life might still call home. What are the best spots? And what are our chances of finally answering that all-important question? Are we alone? I'm Paul Sutter, and I'm a cosmologist. Let's talk about the universe. Mars is by far the most Earth-like planet in the solar system, but that's not saying much. There are two major things helping Mars in its case to support life. One, it's a heck of a lot cooler than the hellscape that is Venus, so there are simply more chances and opportunities for life to, not be incinerated, which is a major plus. Two, we know that in the distant past, Mars wasn't just a little bit Earth-like, it was very much Earth-like. We know that Mars hosted oceans, rivers, lakes, streams. It had a thick carbon dioxide-rich atmosphere. Billions of years ago, Mars and Earth looked like siblings. Yes, the red planet was likely cooler than the Earth, which meant it probably sported much larger polar ice caps and was much drier, but all conditions were definitely in the range for supporting life. And at that same time, billions of years ago, we know that microorganisms roamed or floated or flagellated or whatever it is that microorganisms do on the Earth. So was Mars alive in the distant past? Have any remnants survived to the present day? Or is there at least a fossil record remaining that we could find someday? Since Mars is the closest thing any world of the solar system comes to the Earth, we have the best chances of finding the closest analogs to Earth-like life here. And so in our assessment of Mars as a past or present abode for life, we need to evaluate conditions based on 4 criteria. 1, we need water. The liquid kind, the universal solvent. It can't be frozen or evaporated. It has to be available in abundance for life to use. And it has to have the right salinity and pH. Too salty, not salty enough, too acidic, too basic, and life can't function. Yes, many extremophiles on Earth can live in a wide range of conditions, but there's still a limit to what basic biochemistry can handle. Two, life needs the right chemical environment. It needs lots of the good stuff, the elemental building blocks like carbon, hydrogen, nitrogen, and oxygen. And it needs those elements in high enough concentrations and in the right places, as in on or near the surface near bodies of water. And simultaneously, life needs low concentrations of the bad stuff, the heavy metals like zinc and nickel. Life needs some of those to function for sure, but too high concentrations lead to a toxic environment. Next, life needs energy, just straight up energy, a power source. This can be the sun. It can also be geochemical, like hydrothermal vents. It also needs oxidants and reductants. It needs chemical pathways so that it can store, transform, and use energy. Lastly, the physics has to be right. It can't be too hot or too cold. The pressure can't be too high or too low. Life isn't going to have a great time in the vacuum of space or the core of a planet. There can't be too many cosmic rays, which are really good at destroying vulnerable molecules. It needs a substrate, something to anchor onto. It needs transportation so that it can encounter fresh resources. Life is needy. And while we know for sure that past Mars certainly ticked off some of these boxes, we don't know if it ticked off all of these boxes. And even if all the conditions were met in the past, we don't know if life is guaranteed to happen or has a chance of not making it. As for today, the environments on Mars that could potentially support life are few and far between, and it's all about following the water. Mars still has plenty of water, but it's almost all frozen in either the polar ice caps or under the surface. But over the years, there has been a fair amount of evidence that there may be pockets of liquid. For example, in 2018, researchers found what they believe to be a liquid water lake buried under the southern polar ice cap, kept liquid by the pressures of the cap above it. This discovery was based on radar mapping taken with the Mars Express orbiter. However, further research has cast doubt on whether liquid water is the best interpretation of those radar signals. And then there's everyone's favorite, which are the recurring slope lineae, which are tapered dark streaks that appear on some crater walls in the summer months, which were discovered in 2015. One possibility is that these are caused by underground water thawing and coming to the surface, although there are other possibilities like moisture being pulled out of the atmosphere or just sulfates and chlorine salts combining to create grains that roll downhill. The last place where we might find water on Mars, and hence where life could find a home, is deep underground. In 2024, scientists at NASA concluded that strange seismometer readings were consistent with liquid water in the crust at depths of 10 to 20 kilometers. This wouldn't be a vast underground ocean, that's coming up with another world, but hydrated minerals, little bits of water tucked into crevices and rocks kept warm by the residual heat remaining down there. We know that life on Earth ekes out an existence under similar conditions. So perhaps ancient Martian life migrated down there as the planet cooled and dried, much like Venusian life may have made its way to the clouds as that planet heated up. NASA's Perseverance rover is currently crawling around Jezero crater at the edge of an ancient lake, looking for signs of past life, while the European Space Agency's Rosalind Franklin rover is hoping to reach the surface in 2028. The next stop on our tour of potential life in the solar system is Venus, which on the surface, welcome for the joke, is not even close to being hospitable for life. This planet has by far the hottest surface temperatures in the solar system, beating even Mercury, even though Venus is twice as far away from the sun. That's because of a runaway greenhouse effect, which unfolded, we're not exactly sure when, but somewhere between a few 100 million and a few billion years ago. There's a debate here, but it doesn't matter when exactly this happened for our purposes. What matters is that it did happen. And now the planet is choked to death in its own noxious atmosphere, with atmospheric pressures at the surface over 900 times greater than the Earth at sea level. So super high pressure and temperatures anywhere from 900 degrees Fahrenheit, that's 480 Celsius on the high end, to a balmy 847 Fahrenheit or 450 Celsius on the cool end. Here's the thing. There's no version of any kind of life in any form that we can possibly imagine existing under those conditions. I know that the universe is larger than our imagination, and there's always room for surprises, but even that's stretching it a bit. No, where we're really interested with Venus is in its atmosphere. The higher up you climb in altitude, the cooler the temperatures get until you're all the way in space, which is also bad, but in the opposite way as the surface. But right in the middle, at an altitude between 50 and 60 kilometers, the temperatures are fine, comparable to the range of temperatures that we see on the Earth. And the air pressures are fine, comparable to the range of pressures that we see on the Earth. The atmosphere itself, however, is not so fine. It's mostly carbon dioxide, which, hey, is what plants crave, but also has a lot of nitrogen. And ultraviolet radiation breaks down the molecules in the upper atmosphere to make a host of really nasty stuff like sulfuric acid, hydrogen sulfide, and chlorine. So yes, you could walk outside and breathe the air, and it would dissolve you from the inside out. Life in the atmosphere of Venus has to have a really strange biochemistry. And recently, a group of astronomers claimed to detect the presence of large quantities of phosphine in the Venusian atmosphere. Now, phosphine is an interesting molecule. It's quite stinky, and on Earth, it's a byproduct of anaerobic bacteria, which is part of the reason that marshes and swamps are less than pleasant places to visit. There are ways to produce phosphine without bacteria. And in fact, Jupiter makes loads of it all the time because of that planet's super high temperatures and pressures, properties that Venus lacks. Plus, phosphine breaks down easily in ultraviolet light. So for it to be present in great quantities means that it has to be actively replenished and produced. You smelling what I'm selling? That's right, it's an ad for Patreon. That's patreon.com/pmsutter, where you get to support this show and keep it going. I truly appreciate all of your contributions. That's patreon.com/pmsutter. There's a link down below. Just kidding, I'm talking about the potential life in the clouds of Venus. Cue a giant mess. The news caused a tremendous uproar, with outlets around the world picking up on the tantalizing possibility. But then those pesky other scientists shot back, arguing that the original research was flawed and used an improper analysis of background noise. Then the original authors updated their results and doubled down. Then the astronomers working with the telescope itself chimed in. Then others claimed that the signal was just getting confused for sulfur dioxide. Then, like I said, a giant mess that even today isn't fully resolved. From what I can tell from the literature, the general stalemate sort of community consensus is that Venus probably doesn't have phosphine, and if it does, it's at levels far lower than the original claim. Case closed? Not quite. NASA is developing two Venus missions to investigate further. Because honestly, there's only so much we can get from remote observations. And the small scattering of probes and by that I mean the Soviets, have been able to squeeze down to the surface for short-term visits. One mission will be an orbiter and an atmospheric probe, and the other will be only an orbiter designed to map the surface in high resolution, which will also tell us a lot about the atmosphere. Don't worry, both missions have been delayed because NASA is kind of going through a thing right now. The prospects of life on Venus seem rather low, but it's not zero. And long ago, before the greenhouse catastrophe, Venus was likely very similar to the Earth. After all, we're made from the same material and have very similar properties. It's not an outrageous stretch of the imagination. And some strange form of life may have gotten a start and evolved to adapt in the changing climate. Venusian life couldn't use water. It's way too hot for that. but they may have used droplets of ammonium sulfite or sulfuric acid dispersed throughout the Venusian clouds. This life would be extremely simple, perhaps even lacking cell membranes, and just consisting of self-replicating molecules that use UV radiation as a source of energy. This life may alter the chemical composition of the Venusian atmosphere, explaining several mysteries like the extra oxygen in the cloud layers and extra amounts of sulfur dioxide where it shouldn't be based on simple chemical and atmospheric models. I suppose it's worth a closer look after all. Number 3 on our list of potential homes for life in the solar system is Europa, which I have to admit, I've always had a soft spot for, even as the years go by and the chances of life appearing on that world have been on a bit of a backslide. The reason that I always smile when I think of Europa is because of how surprising it is. We're talking about the second moon of Jupiter, just a little bit smaller than our own moon. It sits just over 750 million kilometers from the sun. At that distance, the sun is less than 5% of the brightness that it is here on the Earth. Europa is cold and desolate and inhospitable. There's water on Europa for sure. Water is by far the most common molecule in the entire universe, so it's not exactly hard to come by, but all that water is frozen. The entire world of Europa is covered in a sheet of ice tens of kilometers thick. But Europa has a surprise. Tidal forces from Jupiter stretch and squeeze the moon on its elliptical orbit. This heats the interior, keeping it molten. And so you'll have a molten interior and a frozen exterior, which means in the middle, you have an ocean. A globe-spanning liquid water ocean, an ocean with more water than the Earth has, an ocean that is completely and totally alien to anything we experience or encounter on the Earth. It is forever blocked from sunlight, with a depth reaching for up to 100 kilometers. Life as we know it needs water, and Europa's got that in spades. But life needs much, much more than water, which is where we start running into trouble with this little moon. First is an energy source. Sunlight is definitely not going to be an option here. But while the vast majority of life on Earth ultimately derives its energy from the sun, there are other creatures that don't. For Europa, the closest analogs we can find are the deep sea hydrothermal vents. These are fissures in the ocean floor where superheated mineral-rich gases escape into the ocean. At the bottom of the food chain here are chemosynthetic microorganisms that get their energy from inorganic compounds like hydrogen sulfide and ammonia. From there, you can build entire communities like tube worms and crabs that are totally fine living life without the sun. For this to happen on Europa, the rocky mantle has to be geologically active. You need fissures and cracks and heat to keep this process in motion. Remember, life needs an energy source. If the mantle is cold and inert, then you just have liquid water meeting sterile rock, and not much interesting chemistry, let alone biochemistry, can take place. We know that the deep core of Europa is molten, but we don't know about the rest. It's hot, but maybe not that hot. Any liquid hot magma needs to be big and buoyant to be able to reach the outer edge of the core and break through the rock barrier. Computer simulations have shown that maybe there just isn't enough magma to do it. But these are just simulations, which, and I'm saying as an expert in physics simulations, aren't, well, let's just say they're rarely the final word on any subject. If the core ocean boundary is active, then Europa has 3 of the 4 needed for life boxes checked. There's water, there's energy, and there's physics. But what about nutrients? Earth has so many opportunities to create rich chemistry, to make a huge variety of chemicals and molecules and reactions and interactions. A lot of this is ultimately powered by the sun. Europa has fewer chances to create chemistry and mix around an abundance of good elements while eliminating the bad. One trick that Europa might have up its sleeve is from its outer surface. Dust can settle on the ice. Then ultraviolet radiation from the sun and cosmic rays from deep space can strike those dust grains, transforming them into interesting combinations. Then, because the surface isn't static, some of these molecules can work their way down into the ocean, which means life may instead find a home clinging to the bottom edge of the ice sheet, not on the ocean floor. There are a lot of open questions here. The European Space Agency's JUICE mission is en route right now, and it will soon be joined by NASA's Europa Clipper. These spacecraft will study Europa in more detail and hopefully splash through one of the occasional ice plumes that eject from the surface. Who knows what they'll taste? Let's finish up our tour of the solar system by getting weird. We assumed at the beginning that life requires water. Every single organism on Earth, no matter the biome, the kingdom, the domain, whether it's an extremophile in a hot spring or some lithotrope buried in the crust, depends on water. Water is the universal solvent. Life is ultimately a series of chemical reactions, and those chemical reactions need to take place in a medium. Water is a great choice because it's abundant, it's liquid in a wide range of temperatures, it's liquid in warm temperatures, which means there's plenty of energy to go around, it dissolves a wide variety of molecules, and well, I could spend an episode singing the praises of water. But water's not the only liquid in the universe. And our fourth potential home for life, Titan, has no liquid water whatsoever on its surface. But it does have lakes, seas, oceans, rivers, streams of methane and ethane. Titan is a world unlike any other. It's the largest moon of Saturn, and it's even bigger than our own moon. It's the only rocky world in the entire solar system, aside from Venus and the Earth, to host a substantial atmosphere. It's so substantial that the air pressure on the surface is 50% greater than that of the Earth's, despite the fact that Titan is much, much smaller than our own world. That atmosphere is almost entirely nitrogen with a sizable fraction of methane. But UV radiation from the sun reacts with that nitrogen and methane to make a wide variety of other molecules, including acetylene, cyanogen, benzene, propane, and propane accessories. And all of this is operating at a temperature of around negative 180 degrees Celsius, around negative 300 degrees Fahrenheit. Like I said, there's nothing like Titan. At these temperatures and pressures, the methanes and ethanes remain liquid. And it's possible, and I want to emphasize that the word possible is doing a lot of heavy lifting here, that those liquids can serve as a solvent for life. Titan has it all. Not water, but a liquid solvent for life's playground. It has an abundant source of energy, namely UV radiation from the sun. It has an extremely rich chemistry with a wide and diverse array of compounds. And it has the physics, temperatures, and pressures that allow complex chemistry to take place and movement of materials through precipitation and wind to mix them up. If there's life on Titan, it's different from any Earth-like life at a deep, fundamental biochemical level. This isn't water-based life, it's methane-based life. Instead of consuming oxygen or carbon dioxide, methane-based life would consume hydrogen or acetylene. In fact, evidence from NASA's Cassini spacecraft and the Huygens probe, which landed on the surface in 2005, reveal production of both hydrogen and acetylene in the atmosphere, but then a lack of it near the surface. Sure, there are plenty of ways to scrub those out of the atmosphere at lower altitudes, but maybe, just maybe, it's getting eaten. In fact, it might even be possible to build cell membranes using the exotic chemistry on Titan. On Earth, most life uses phospholipids to build membranes, but those are in short supply in the cold, toxic environment of Titan. Instead, life on Titan could build what are called azotosomes, which are membranes made of acrylonitrile. Although other research suggests that those compounds just form ices instead of flexible, semi-rigid membranes. Life on Titan wouldn't exactly be thrilling. I mean, it would be exciting to find, but the extremely low temperatures prevent rapid metabolisms. Almost certainly, if there's life, it's so extremely simple and slow-acting that it just might be unrecognizable. But if that's not enough, Titan has a secret. The atmosphere and lakes of methane sit on top of a crust made of water ice. And some computer models suggest that there is a liquid water ocean hiding underneath that crust. This ocean wouldn't be as nice and pristine as the one on Europa, as it would likely be extremely rich in ammonia. On Earth, this would be a completely toxic environment. So on Titan's possible ocean, life wouldn't have to just overcome the lack of sunlight, but also a challenging environment to support biological functions. But hey, we can't rule it out, at least not yet. In 2028, NASA plans to launch the Dragonfly spacecraft to Titan, which is a rotorcraft designed to land at sites, study them, and then hop up to another location. As with all the other missions designed to hunt for life, the hopes of actually finding it are honestly slim. But no matter what, we're going to learn a lot about chemistries on worlds other than the Earth, and we may even learn about how life got its start on the Earth. But that's another episode. I know I left out most of the solar system. Who knows what's going on in the depths of the gas and ice giant planets? Europa isn't the only water world. It's joined by Ganymede, Enceladus, and others, maybe even Pluto. Maybe microorganisms can eke out a living tucked in a crater on an asteroid or comet, or have some sort of agonizingly slow metabolism attached to ice and dust grains beyond the orbits of the planets. We don't know the variety of forms that life can take. We haven't seen any obvious signs of life, but in all honesty, we're just getting started in a serious, systematic, scientific way. The universe has surprised us before, and we have to be prepared to be surprised and delighted again. So what do you think? Which one of these four worlds, Venus, Mars, Europa, and Titan, do you think has the best chances for hosting life now or in the past? And has the best chances for us finding that life? Or is the rest of the solar system dead, and we have to look further afield to the exoplanets to find our siblings among the stars? Let me know what you think in the comments. Thank you for watching, and we'll see what the future will bring.